What up, friends? Today is Unit 12, Day 13. It is Monday, April 20th, 2020. Yes, you can giggle at 4:20 because you're home alone right now, and it's okay. You need to take out Unit 12 Kinetics and Equilibrium note packet along with a piece of scrap paper. Today we're going to finish kind of the rest of equilibrium. So we're going to finish off LeCharlier's principle, and we're going to do a couple of practice problems. You will have some practice tomorrow as well. So today you don't have a skill check. Tomorrow you'll have a longer skill check on LeCharlier. So really we're going to finish up, and then we're going to do some practice. I did want to start today with a warm-up problem based on yesterday. Anyone know who this is down here? Justin Timberlake. Anyone ever hear the song It's Gonna Be May? I think you should listen to it while you do this or after. Anyways, so you can do this practice problem on a blank sheet of paper. You can do it really anywhere, but this is based off of yesterday. So over the past 2 days, we've been looking at LeCharlier's principle and seeing how concentration, either increasing or decreasing for reactants or products, causes a shift in equilibrium. Then we looked at temperature, how increasing or decreasing temperature can cause a shift. Remember, both of those apply that kind of phrase, add away, take towards, to figure out which way the equilibrium shifts. And then we looked at pressure. Now remember, pressure is only going to affect systems with gases, and that's the one where you count the moles of gas on the reactant side and product side, and based on moles of gas, and if a pressure is decreased or increased, you're going to shift. Today we're going to do catalyst, but before that, I wanted you to work on these two problems that are based on the same reaction up above. You can pause the video if you want. I'm going to go over these. So we've got, on the reactant side, you've got heat plus 2 moles of water in the gaseous phase, yielding 2 moles of hydrogen gas and 1 mole of oxygen gas. It's a double-sided arrow. And the first question says, if the temperature is decreased, what direction does the equilibrium shift? Now remember, temperature is like concentration. So this is where you can use add away and take towards. So we're decreasing the temperature. Kind of like a minus. So I'm going to go to where the heat is, which is going to represent something that would change because of the temperature, and I'm going to write a subtraction sign. So I'm taking away the heat. I'm decreasing the temperature. So remember, take towards. So that means the new arrow I draw over the existing old arrow needs to point towards what I took away. So if I want it to point towards this minus sign, it's got to point to the left. So this is a left shift. What that would mean was the concentration of these two things goes down and the concentration of this goes up. So that's the first one. I'm going to erase this now. The second question says, if the pressure is increased, what direction does the equilibrium shift? Pressure you cannot use add away and take towards. Remember, pressure is where we're going to be looking at moles of gas on each side of the reaction. So if I take a look, I have 2 moles of water on the left, on my reactant side, and I have 2 moles of gaseous hydrogen and then another 1 mole of gaseous oxygen for a total of 3 moles on my product side. Now, I am increasing the pressure. I'm squeezing this system tighter and tighter. That means my equilibrium is going to shift towards the side where there is less stuff or less moles. So I'm going to shift to the left. So the answer here, shift to side with less moles of gas. So that would be a left shift. So both of these demonstrate a left shift. So that's kind of applying what we did yesterday. What I need you to do now is I need you to take your packet out to page 12, or not 12, excuse me, 15. We're actually going to finish up the notes for this unit. So we're going to do the last of the LeCharlier stresses, which is a catalyst, which is nice because this is the easiest one. So we've done temperature, we've done concentration and pressure. Now we're going to look at what if you had a catalyst to the system. And once we're done with this, there's going to be a guided practice problems on the bottom of page 15. And I'm going to give you some problems to do on scrap paper by yourself. So a catalyst, right? A catalyst we heard about when we did potential energy diagrams. A catalyst lowers the activation energy. So remember, it lowers activation energy. I don't know why that's making a highlighter. It makes a different pathway. But the good news is for LeCharlier's principle, adding a catalyst changes both the forward and the reverse reactions equally. So it speeds up the forward at the same rate that it speeds up the reverse. So that means when a catalyst is added, there is actually no change to any of the equilibrium concentrations, which means there is no shift whenever they ask what happens when a catalyst is added. So for a catalyst, your answer is no shift. It doesn't go left, it doesn't go right, it doesn't change the concentrations of anything, because remember, you're always starting and ending on your potential energy diagram at the same place, regardless if you add a catalyst or not. So it doesn't change the concentrations of anything. So now you've got concentration, temperature, add away, take towards. You got pressure, where you look at moles of gas, and now you have catalysts. So I'm going to summarize that down here. So a summary of your stresses. Stresses 1 and 2 were concentration and temperature. To help you remember, add, away, take towards. So those are the stresses where you're going to apply that rule. For pressure, you look at moles of gas on the reactant side and the product side. And then for a catalyst, it's always no shift. No change in concentration, no shift. Anything like that. Now what we're going to do is we're going to do a big practice problem together, and then I'm going to give you one to do on your own. This practice problem is at the bottom of page 15. It gives you a reaction, and then it gives you a bunch of different stresses, and it wants you to indicate which way it shifted. Then it wants you to tell the effect on the concentration of something. So let's start with the first one. This says, the first stress, what if we add CO? So this is a change in concentration. So we can use add, away, take towards for this. Okay, so we're going to add CO. So I'm going to find CO on here, and I'm going to put a plus sign over it. Add. I know that I need to shift this original arrow so that it now points away from what I added. So remember, add, away. That means my arrow is going to shift to the right so that it shifts away from what I just added. So if I add CO, I shift away, which is to the right. Always draw your new arrow over the old one. Don't draw it over here somewhere. You'll confuse yourself. All right, now what's that going to have an effect on the carbon dioxide concentration? Okay, well, here's carbon dioxide. Let's look at our new arrow. Is it pointing at carbon dioxide or is it not? Well, it's pointing at carbon dioxide, meaning that we're using up more of these to generate more of this. So the concentration of that will increase. Good. All right, let's look at our second one. So I'm going to erase these. Second stress, add I2. So this is increasing a concentration. So remember, concentration and temperature, you can use the add away. So I'm adding away. That means when I add something, my arrow should shift away. So I'm adding I2, so I'm going to put a plus over the I2. I know my arrow needs to shift away from what I just added. So my arrow is going to point away from that, which is to the left. Now, what's that going to do to my concentration of CO2? Let's look at this new arrow. It's pointing at these two. That means that the carbon dioxide concentration, since this arrow is not pointing at it, it's being used up to create more of this. So its concentration is going to decrease. So unless the new arrow you draw points at your substance that you're being asked about, the concentration goes down. So this new arrow does not point at carbon dioxide. Good. All right, so I'm going to erase those. Let's look at our third stress. What about if I remove heat? Okay, heat, temperature. I'm allowed to use the add away, take towards. I'm removing, which means I'm taking away. So that means my arrow needs to point towards whatever I take away. So heat, all right, well, let's find heat on here. Kilojoules, that's a measure of heat. So I'm taking away heat or removing, so I'm going to put a minus sign. My new arrow that I'm going to draw over my old one has to point towards what I took away. So I took away heat, so my new arrow needs to point towards that, which is to the right. Now, what's that going to do to my concentration of I2O5? Well, here's I2O5. The new arrow I just drew points away from that, which means this is being used up to create more of these products. So this concentration is going down, because my new arrow doesn't point at it, so it must be being used up. Good. All right, let's take a look at pressure. Remember, this is increase in pressure. Pressure we cannot use add away and take towards like we could for concentration or heat. Pressure is where we look at moles of gas on each side. So if I look on the reactant side, I have 5 moles of carbon monoxide and then 1 mole of I2O5. So that's a total of 6 moles of gas on my reactant side. And notice these are gases. Let's take a look at my product side. I have 1 mole of I2 gas, 5 moles of carbon dioxide gas. That's a total of 6 moles. Hey, the moles on the left are equal to the moles on the right. So that means that increasing the pressure is not going to shift anything at all. So I'm going to write no shift. Same number of moles on reactant and product side. So because the moles of gas are the same on each side, there's no shift at all, which means the concentration, there would be no change. It's constant. Good. And let's look at our last stress for this reaction. The last one says remove I2. So this is a concentration one. So this is where you can use add away and take towards. So I'm removing, so I'm taking away. That means my new arrow should point towards what I took away. So I2 by itself is right here. So I'm going to put a minus sign because I took it away. My new arrow points towards that. So it's going to show a shift to the right because now this arrow points towards what I took away. Now, what would that do to the concentration of carbon monoxide, CO? Well, here's CO. The new arrow I just drew points away from that CO, which means the CO is being used up to generate more of these. So the concentration is going to decrease. So this is an application of most of the different ones we looked at. We looked at concentrations in here, we looked at pressure, and we looked at heat. Now the last problem in your note packet gives you this reaction right here, and it says, increasing the pressure on the reaction would cause what to occur? Okay, so these are kind of a little bit trickier. So let's take a look. If I increase the pressure, let's first figure out which way it's going to shift. Remember, when you're looking at pressure, you're looking at moles of gas. So on my reactant side, I have 2 moles of gas, and on my product side, I have 3 moles of gas. All right. Remember, if you increase the pressure, you're squeezing the system tighter. It's going to want to shift in a direction where there are less moles. So it's going to shift to the left. Now, when it shifts left, it's going to decrease the amount of these, the NO and the O2, and it increases the amount of NO2 because the new arrow always points towards what's going to increase in concentration. So let's read these 4 options and see what happens. Is the amount of NO going to increase? Nope, because my new arrow doesn't point at NO, it points away from it. So NO is actually going to be used up to produce more of this, so that's out. Will the amount of NO2 increase? Well, yeah, because my arrow that I just drew is pointing at that, demonstrating that these are being used up to create more NO2. So that's true. Let's look at choice C. Would nothing happen? No, something definitely is going to happen. And then D, the amount of O2 increases. Well, my new arrow doesn't point at O2. O2 is over here, which means it's being used up. So that's not true. So your answer is B. So in this example, you got to actually figure out which way it shifts first and then figure out which one of these is true based on that shift. So that's a little bit trickier. What I'd like you to do now, take out a scrap piece of paper. We're going to go through an example problem like the one up here, and you're going to do it step by step on your own. So you're going to pause the video kind of as we go through this example. So here is the first reaction. And I'd like you to try this out. If I add chlorine to this reaction, I want you to tell me which way will it shift and what will it do to the concentration of PCl5. So you can pause the video. Okay, so if I add chlorine, this is a concentration problem, so I can use add away. So if I add chlorine, I'm going to put a plus sign over the chlorine. My new arrow needs to shift away from what I added. So over my old arrow, I'm going to draw my new one. So it shifts away, so it shifts to the left. What does that do to the PCl5? Well, these are now being used up to generate more of the PCl5 because my new arrow points at what is increasing in concentration. So I would say increase. Good. All right, let's look at a second problem using this same reaction. So what would happen if I remove PCl3? Which way would it shift? And what effect would that have on your concentration of chlorine? So pause the video and try this problem. All right, so I'm dealing with concentration, so I can use add away and take towards. Well, I'm removing, so that's taking away. So that means take towards. I'm removing PCl3, so I'm going to make a minus sign over the PCl3 to show I'm removing it or taking it away. And that means the new arrow I draw over my old arrows has to point towards it. Make sure you're always drawing your new arrows over the old ones, not like shifted over here somewhere. So my new arrow has to point towards what I took away, which would mean to the right. So that's a right shift. Now what does that do to my concentration of chlorine gas? Well, these are now being used up to produce more of this. My arrow points now at what I'm producing more of. So this would increase in concentration. Good. All right, let's take a look at this one. Same reaction. What happens if I increase the temperature? Which way will it shift? And what happens to PCl5? Remember, temperature has the same rules as concentration. So you can do, I'm increasing, which means I'm adding, which means my arrow will shift away. So we got to deal with temperature now, or heat. So we got to find where our heat is. Here's my heat, and I'm increasing it. So I'm going to put a plus sign. I'm adding heat. That means my arrow is going to shift away. So my arrow is going to shift away from what I added, which would be pointing to the right. What does this do to my amount of PCl5? Well, if I'm shifted to the right, I'm using up more PCl5 to create more PCl3 and Cl2. So I'm actually decreasing my concentration of this because I have to use it up to create more of these two. Remember, the arrow points towards what's increasing in concentration. Since this new arrow I drew isn't pointing at this, that means it must be decreasing in concentration. Good. All right, what about adding pressure? Okay, so remember, add away, take towards only works for temperature and concentrations of reactants or products. When we're dealing with pressure, you got to look at moles of gas. So pause the video, try this problem. All right, so if I look on my reactant side, I have a gas right here, and that's 1 mole of gas. I don't have any other reactants that are gases. On my product side, I have 1 mole of PCl3 and 1 mole of Cl2. They both have coefficients of 1 for a total of 2 moles. So if I increase the pressure, I'm squeezing my system tighter and tighter. It's going to shift to relieve that. So it's going to go to the side with less moles of gas, which would be to the left. What does that do to my concentration of Cl2? Well, my new arrow is pointing away from that now. So this is being used up to generate more of the PCl5. So its concentration is going to decrease. All right, I think we have a couple more. All right, what about if we remove pressure? Let's try this one. Remember, once again, pressure, you got to use moles of gas. So pause the video and try that. So same as before, we had 1 mole of gas on the left, 2 moles on the right. If I'm removing the pressure, I'm relieving the pressure. I can shift to a side with more moles of gas, which would be to the right. That would cause my concentration of PCl5 to go down because my new arrow is pointing away from it. It's not pointing at it. I'm using up more PCl5 to create more of those. And then the last one. What would happen to that reaction if you added a catalyst? So pause the video. Remember, a catalyst, no shift. That's always your answer. It increases the forward at the same rate as the reverse. So it's not going to change concentrations of anything. It's simply no shift. Good. So you can kind of see how you can apply all of the different stresses to one specific system. You can apply different changes in concentration, temperature, pressure, and then a catalyst. And then the last question, this is a challenge question. Try it out. It says, given the following balanced reaction, which of the following stresses would cause the concentration of H2 to go up? So pause the video, and I specifically bolded the word cause the concentration of H2 to increase. I'm not telling you you're adding H2. I want to know which of those 4 options would cause the concentration of H2 to go up. So pause the video. Okay, so there's a couple ways you can do these problems. If you're thinking about it, remember I said that whatever way your arrow shifts, and this should be a double-sided arrow, whatever way your arrow shifts, it will point towards whatever's increasing in concentration. So if I want H2 to end up increasing in concentration, I want my arrow to end up pointing to the left. That's one way you could think about it. So you need to think about which of these possibilities will cause the reaction to shift to the left. Or you can kind of do process of elimination. You can figure out for each of these, is it going to shift left or right? And then pick the one that's different than the others. So let's look at this. It says increase in pressure. So remember, pressure is moles of gas on each side. So I have a total of 3 moles of gas on the left because I look at the coefficients for the gaseous substances. And notice on the right, I don't have any moles of gas. I have liquid. So this is 0 moles. So if I increase the pressure, it's going to shift to the side with less moles of gas, which is going to be to the right. All right, let's take out our second option, add a catalyst. A catalyst doesn't shift anything at all, so it's never going to change the concentration. So anytime a catalyst is an option and they want to know if the concentration is going to change, that's automatically out. Okay, what about decreasing the temperature? All right, so temperature, here's my temperature, here's the heat. Remember, for temperature, you can use add away, take towards. So decrease, I'm taking away temperature. That means my arrow needs to shift towards it, which would be to the right. So that would be a right shift. Okay, now let's look at our last option, remove O2, right? So add away and take towards works for that. So I'm going to remove O2. If I take, it shifts towards, which is to the left. Notice if I shift to the left, I'm going to increase the amount of H2 that ends up being produced. This question does not say what happens when you increase the concentration of H2. It says, what can you do to end up increasing that? And if you look, you can do process of elimination. The first choice, your option was to shift right. Second one, catalyst is never going to cause a shift or any change in concentration, so automatically eliminate that. Choice 3 was shift right. So really D is the only one that's different from those 3. So it's choice D. Another way you could look at it is it should shift left to increase the amount of that, and the only one that shifts left is the O2. So that's a challenge problem. You're going to have some skill checks tomorrow that are a little bit longer working on LeCharlier. Please be sure to write in the discussion post if you have any questions or send me a message. I know it's a little tricky. Adios.